It's funny. We see magnets every single day, right? They're on our fridges, they're inside super fast trains. They have this invisible, almost magical pull. But have you ever really thought about what's going on inside one? Where does that force actually come from? Well, that's what we're going to do. Let's dive in and uncover the secret of the magnet. Okay, to kick things off, just look at this picture. What you're seeing are tiny little iron filings scattered around a simple bar magnet. And you can see they're not just a random mess, right? They're actually tracing out the invisible architecture of the magnetic field. This beautiful pattern, this is our very first clue. It shows us there's a hidden structure, a force that literally reaches out into the space all around the magnet.
All right, so before we get to the really deep secret, we've got to cover the basics. Let's just quickly go over the rules of the game, the stuff you can see and feel for yourself when you play with magnets.
So the rules are pretty simple, stuff you probably learned in school. Every single magnet has two ends, a north pole and a south pole. If you put two north poles together, they push each other away. Same with two south poles. But bring a north and a south pole close, and they snap together. It's this simple dance of push and pull, and you usually see it with iron magnets. But this simple behavior, it stumped scientists for centuries. Okay, now for a question. It seems really simple, but the answer just blows the whole thing wide open. Let's say you take a bar magnet. It's got its north pole on one end and its south on the other. What happens if you snap it right in the middle? Do you get one piece that's just a north pole and another piece that's just a south pole? Well, the answer is nope. You actually get two brand new smaller magnets, and each one has its own north and south pole. And if you cut one of those in half again, you get two even smaller magnets. Do it again and again, you'll always end up with a smaller magnet that has two poles. You can never get a north pole all by itself. And that right there, that's a huge clue.
This whole idea leads us to a concept called a magnetic monopole. It's a hypothetical particle, a tiny magnet that's only a north pole or only a south pole. But here's the thing, and this is absolutely critical. We have never, ever found one. They just don't seem to exist. And their absence is one of the biggest puzzles in physics. It's totally central to understanding what magnetism really is.
Okay, so if we can't isolate a single magnetic source, like a monopole, how in the world do we map out this invisible force? Well, we go right back to that picture with the iron filings, but we make it a bit more formal. We use an idea called magnetic field lines. Now, these imaginary lines have a few important rules. They never cross each other, and the denser they are, the stronger the magnet. But the most important rule, the one that changes everything, is that they always form continuous closed loops. They flow out of the North Pole, loop all the way around back into the South Pole, and then keep going right through the inside of the magnet to make a complete circuit. They never just start or end in the middle of nowhere.
And this is where things get really, really interesting, because this is totally different from electricity. See, electric fields are simple. They start on a positive charge and they end on a negative charge. There's a clear beginning and a clear end. But magnetic fields? Nope, they just loop around forever. That closed loop thing is the whole key to the puzzle.
This idea is actually so fundamental, it's enshrined in one of the most important laws in all of physics, Gauss's law for magnetism. Now, that sounds complicated, but all it really means is this. If you imagine drawing a bubble anywhere in space, any magnetic field line that goes into the bubble must also come back out. The net change is always zero. There are no sources, no starting points, and no sinks, no ending points for magnetism. Okay, let's put the pieces together. We know there are no magnetic monopoles, and we know the field lines always form these closed loops. So, the big question is, what in the world could create a field that behaves like that? Well, take a look at this. On the left, you've got your standard bar magnet. On the right, that's a coil of wire. We call it a solenoid, with an electric current flowing through it. Just look at their magnetic fields. They are almost identical. This isn't a coincidence, folks. This is the smoking gun. This is what solves the entire mystery. And the big idea came from a guy named André-Marie Ampère, way back in the 19th century. His thought process was brilliant. He said, look, if a current flowing in a loop of wire creates a magnetic field, what if all magnetism is just created by tiny circulating currents? And it turns out he was absolutely right. This is the secret. The true origin of every single magnetic field in the universe, from that magnet on your fridge to the giant one protecting our planet, is one thing and one thing only: moving electric charges. Now you might be thinking, wait, There's no battery in a bar magnet. And you're right. The current comes from the electrons themselves, spinning on their axis and orbiting the nucleus inside every single atom. Each of those tiny motions is like a microscopic loop of current. And when enough of them line up and point in the same direction, boom, you get a magnet. So now that we know the secret, that it's all about moving electrons, we can finally understand why some materials stick to magnets and others don't. It all just comes down to how those tiny atomic-level currents decide to organize themselves. And basically, we can sort all materials into 3 main flavors of magnetism. Okay, so here are the 3 big categories. First, you've got what's called diamagnetic materials. These are actually weakly repelled by magnets. Then you have paramagnetic materials, which are weakly attracted. And finally, you have the heavy hitters, the ferromagnetic materials. These are the ones we all know and love, the ones that are strongly attracted to magnets. Let's break those down. First up, diamagnetism. Believe it or not, this is kind of the default state for all matter. It's a super, super weak repulsion from a magnetic field. And when I say all matter, I mean everything. Water, copper, even you. You are slightly diamagnetic. It's just that the effect is so incredibly weak that it's usually completely overshadowed by other things. All right, next we have paramagnetism. Think of materials like aluminum. In these, every single atom is already its own tiny little magnet. The catch is they're all just pointing in completely random directions, so it all cancels out. But if you bring a strong external magnet nearby, you can coax them into lining up a little bit with the field. This creates a weak attraction. As soon as you take the magnet away, though, poof, they all go back to their random directions. And that brings us to the main event, ferromagnetism. This is the really strong attraction you feel with things like iron, cobalt, and nickel. What's happening here is pretty amazing. There's a special quantum mechanical effect at play that basically makes all the tiny atomic magnets want to line up with their neighbors. They do it spontaneously, all on their own, without any help from an outside magnet. And this picture shows you exactly how that works. See, ferromagnetic materials are broken up into these little magnetic neighborhoods called domains. In a normal, unmagnetized piece of iron, all these domains are jumbled up, pointing in random directions, so the whole thing acts, well, not very magnetic. But the moment you bring a powerful magnet close by, something incredible happens. The domains that are already kind of lined up with the field start to grow, swallowing up their neighbors, and others just snap completely into alignment. Suddenly, billions and billions of tiny atomic magnets are all pointing the same way, creating one powerful, unified magnetic field. So think about how far we've come. We started with a simple bar magnet and those iron filings, and now we're all the way down at the quantum behavior of electrons. To wrap things up, let's look at the absolute most extreme, most mind-bending example of magnetic behavior out there. And this is where things get truly wild. If you take certain metals and cool them down to incredibly low temperatures, close to absolute zero, they become something called a superconductor. Now, that means they can conduct electricity with literally zero resistance, which is amazing on its own. But they also do something else incredible with magnetic fields. They become perfect diamagnets. This phenomenon is called the Meissner effect. A superconductor just refuses to let any magnetic field lines pass through its interior. It actively pushes them out. It expels them completely. And the result? The magnet is repelled so powerfully that it just floats there, levitating on a totally invisible cushion of magnetic force. This isn't science fiction, by the way. This is the exact technology that makes things like maglev trains possible. And that brings us full circle right back to where we started. Our entire beautiful understanding of magnetism, the idea that it all comes from moving charges creating closed loops, is built on one simple observation. We have never, ever found a magnetic monopole. But what if we did? What if, somewhere out there in the vastness of the universe, a single lonely North Pole exists? Finding one wouldn't just be some little scientific curiosity. It would fundamentally rewrite the laws of physics. We'd have to change the core equations that describe how our universe works. So that's the thought I want to leave you with. What do you think would change if we finally found one?